Hello, everybody. Thanks for coming. My name is Megan Fain. I'm a professor in mechanical engineering as well as ocean engineering. And why we are here is Damian Manda is here for his thesis defense. So before I introduce Damian, I'd also like to introduce his thesis committee. Andy is not here. Andy, are you here?
Can't talk back.
He won't be.
Okay.
Well, we can until the end, but
Okay. Well, Andy's here. Everybody knows Andy. Oh, and Andy.
Andy Armstrong.
Our other thesis committee member is Dr. Martin Rankin, who's coming here from NAVSEA in Keyport, the Naval Underwater Warfare Center, Keyport. Yes. Okay. And I'd like to give special props to Val, although he's not a part of this thesis committee. He was a large part of this research as well. So at this point, I'd like to introduce Damian Manda. He is a master's in ocean engineering, and he's been working on autonomous surface vehicles for the past 2-3 years. He's done a lot of great work. In fact, I'm very tempted to not pass him so that he can stay. So with that, without further ado, I'd like to introduce Damian Manda.
All right, thank you, Professor Thane. So, getting right into it, since everything's kind of been introduced, the first question is kind of why I chose autonomous vehicles to work with. It was something that I'd always been interested in, and it's increasingly become a focus of NOAA and especially of the hydrography side of things where I come from, the ocean mapping. So they present a lot of advantages in terms of operational abilities. So you can run an autonomous boat continuously where you need to switch out a human crew, have people get rest, and usually don't run them overnight for small boats. You could potentially do that with autonomous boats. We can optimize algorithmically the survey methodology so that we can do it as efficiently as possible, saving time and therefore money. One of the most important things is a lot of the areas that we work in are close to shore and some of the most dangerous areas for being on a small boat, and so we can decrease the safety risks to those people that would be working in those environments by setting in boats that don't need to have people on them. And finally, you can have a force multiplier effect by having a single boat or multiple boats operated by a single operator who's on the ship and have them doing the work that would typically have 2 to 3 people on each boat. So to talk a little bit for those who don't know about hydrography, this is ocean mapping, typically using swath sonars that have an angular beam on the seafloor. This means that with depth, the width of the sonar sensing area varies, and so as you go along from shallow to deep, your swath will increase in width, and so it varies as you're surveying an area. And the idea is to be able to compensate for that. So what we do in human operating surveys is we'll divide up an area to be surveyed into polygonal regions, which then are designated to different human-driven launches, and they figure out how to best survey them. This typically results in a methodology where the lines will converge coming into shallower areas and diverge going to deeper areas because of those swath properties. There's been a little bit of work in doing this autonomously, but most of them concentrate on still planning straight line paths. There's been some work, the two in the upper portion here both rely on previous knowledge of both the area and the depth map and still plan linear paths, but the spacing varies depending on the depth. The one kind of body of work that's similar to this was developed by the Navy in conjunction with a surveying firm in the early 2000s and hasn't really been pushed out into the commercial sphere, although there's some software that can plan a basic path following, although it doesn't do it in the same method that mine does. Recently, there's also been some developments with single beam that will automatically designate an area but still run perpendicular parallel paths, which is the methodology that you would do a single beam, but not necessarily applicable to the swath sonar that I'm targeting. The initial areas of application in NOAA for autonomous vehicles have been either nearshore areas that are shallow. We can get small vessels in where we couldn't even necessarily bring a larger survey vessel, or where it would be dangerous if we don't know where the shoals are, or wide open spaces where there's not going to be much other traffic. Your boat's not going to run into anything, but these require higher endurance more robust vessels so that they can operate further away from a mothership. For my research, I've been targeting the nearshore areas and the small boats that are typically battery operated. The priorities of NOAA have also kind of shifted to move towards some of the surveying of shallower areas and things that are good for autonomous boats. This shows an area in Alaska which are increasing in traffic, but mostly unmapped since the 1880s. There's also a lot of areas on the East Coast where there's large amounts of recreational boat traffic, but haven't traditionally been the focus of NOAA, which has been more focused on large ships and ports and areas where deep draft vessels are going. But as everybody gets chart plotters on their boats and tries to drive around on them like people using Google Maps, if the maps aren't right, they're going to run aground because they don't actually know what the current data is. So we need to be remapping those, and it's a lot of area that's very shallow. For my system, I've been trying something that's flexible and somewhat simple to apply to a wide range of vessels, but also low cost so that it can be easily duplicated and used in a research environment. But I'm doing this by kind of simplifying the voltage and interface requirements for the system to minimize the battery capability and have it simple to plug into any vessel and what's available. I'm also reducing the cost by using commercial parts and integrating with open source software so that we don't have to replicate things that have already been done. Going into depth on the hardware, first, we've used a few platforms for this research. The two that I've primarily focused on are the NOAA Emily vehicle here, which was originally designed for ocean monitoring and weather data collection, but have been retasked to a lot of different applications, including mapping. That one I've designed a complete retrofit system for that from the ground up develops autonomy for the vessel. In addition, I've worked with some Teledyne Ocean Science Z-boats, which were bought recently by NOAA for the NOAA ship Thomas Jefferson, and those already have a lot of the surveying and data transfer systems, so I've just developed an autonomy module for that. I've also worked with undergraduate senior projects teams to integrate some of my research on their vessels, such as installing a sonar on their large bass boat that they built this year, and working with them to do similar software for some of the control of their other vessels. For my hardware system, it comes together between a bunch of open source and commercially available parts. The Raspberry Pi is the kind of brains of the system, and everything pipes into there. That's what actually runs the autonomy software and makes the decisions. The Arduino takes care of the sensor output to the actual thrusters and rudder of the vessel. We get positioning information from a GPS unit that's either integrated or, in the case of others, take that from existing systems. There's a long-distance Wi-Fi that then communicates all of the information back to a shore station, so you can both monitor what the vessel is doing and command it to do different tasks. And then in case of human override, there's a hobby RC controller that allows people to drive the boat if it's not doing something that you want it to, or if it's near shore and you're trying to dock it. That all fits together in the complete package here for Emily. We have the one battery pack that can be anything from a 12-volt marine battery. There's a 14.8-volt lithium-ion pack on Emily, and we can integrate with any of those using a number of voltage regulators to get what we need to actually run the interior electronics. An interesting part that I had to add was this isolator board. The systems on board Emily itself tend to be noisy when the engine is operating, and so I developed a custom circuit board to go in there and isolate the signals on the Emily side of things from the autonomy box. And then that has a separate battery pack that runs that. This is what the box looks like assembled. You can see all the components that I talked about in addition to the regulators and that custom PC board that then interfaces with Emily. You can see this interfaces with the native cable that's already on the boat, so it just plugs right into it. And otherwise, the interfaces that are needed come out through power, Ethernet, and there's an external kill switch that allows you to shut off the motor if it's running and you don't want it to, it's not taking commands or something like that. The total cost of the system for everything, so this will retrofit a boat from scratch for autonomy, is about $1,200. The highest cost item on here is the GPS system, so if your existing survey boat has a high integrity GPS, as most of them will, you can take that $400 cost out and build the whole thing for about $800. For the Z-Boat, we created the simplified module. That one just has the kind of the Raspberry Pi system with converters to talk to the systems on board the Z-Boat, as well as there's the summary kind of everything that's on the boat. So we've got already the sonar system, some data transfer equipment, both for cell phone, remote distance, and I'll talk about some work I've done with that later as well. That module, all put together, only costs $223 because we've eliminated a lot of the expensive components, and that allowed me to replicate it a few times so that we could make one for each boat that the TJ owns, as well as spare for troubleshooting. So now that we have all this hardware, we need to actually make the vessel do what we want it to, and so the part of that comes into play is the control system, which will translate what we want in terms of heading and speed into commands for the control surfaces on the vessel. The underlying principle behind this that's been applied is called model reference adaptive control, and it's a type of controller that's designed to change the response based on the way that the vessel itself is operating. So it should be able to compensate for different loads, different weather conditions to some extent, and reduce the amount of human tuning that's needed in the control system. There's two types of controllers that I implemented within this, one of which I focused on more because it was more promising. The first one was a course change controller that uses a specific response between the current heading and the desired heading, and then attempts to follow that. The response is mostly controlled by a damping ratio, zeta, which is interpreted to be the amount of overshoot, essentially, and then you choose a tau, which is the time constant for the response based on physical measurements testing the vessel ahead of time. This kind of shows the effect of zeta, so the zeta below 1 will have overshoot, and you can see that, and then it oscillates a little bit. Zeta equals 1 is critically damped, so it will go to the value without overshooting, and anything larger than that will go more slowly to the final value. The system adapts by changing the constants of a PID controller. So this is a standard PID equation. We have a proportional constant times an error, a derivative constant times the change in error, and integral constant that adds up the error over time. We adapt these based on these laws, which are derived from the transfer function. To see that in a block diagram that might make a little bit more sense, I've divided this up. The adapted portion is in yellow, which is adapting the controller itself in blue. That's the PID controller. Green represents the parts that are actually the system. So while it's there as a block, that's really what we're just measuring from the boat, and that's how we're assuming that it's behaving. The orange is the actual reference model, which is the model reference part of the adaptive control that's running in parallel based on the same inputs, and will hopefully eventually is used to adjust the PID controller constants to keep them in line. There's also a portion that takes into effect some of the nonlinearities of the system. Since we're just doing a transfer function between headings, this doesn't have any knowledge of the fact that a rudder has a limited angle that it can go to. It thinks that you can get more rate of turn just by increasing the rudder. So there's a rate of turn limiter as well as a rudder limiter in there that feed into the PID and model reference controllers, respectively, to limit the rates of turn of those to what's physically possible. A few examples of how that controller works. For an overdamped case, you can see it can follow this pretty well. Red is the model heading transitioning smoothly from the initial to the final heading, and green is the actual heading of a simulated vessel in this case. In the lower portion, the rate of turn, which is what it's basing a lot of the error calculations on, is shown, and you can see how that kind of oscillates based on settings. For this one, I set the adaptive gains fairly high, and so it actually very quickly runs the proportional and derivative constants to 0, which will essentially cause the vessel to stop turning when it's turning too quickly, and then as the model starts turning faster than what that's now doing, not having any rudder on, it'll increase those again to what it needs. In a realistic scenario, you would want these gains to be a little bit lower so that it's not constantly oscillating like that. In an overdamped case, you can see we get the response that's expected here as well, overshooting and oscillating a little bit to get to the final value. The second controller that I used and that has been implemented more successfully for actual vessels is a one that actually changes the ship model itself. This one is based on a linear model called the Nemoto model, which just at an infinity time will have y equal to, so this is the rate of turn equal to a constant times the rudder angle delta. And so essentially there's a tau going to that, and then it eventually gets to a maximum, which is how most ships behave in a first order approximation. We checked with some of the boats that we used to see how accurate this model would be, and it turns out that for these small vessels especially, they do tend to be very linear. So this is the response at a number of different thrusts to rudder angle, and you can see that each of them is linear. There's a proportionality constant in the adaptive system that takes care of the speed, and so it actually adjusts for these thrust offsets. And this goes to the adaptation laws again. You can see they're based on that equation. That's just a rearranging of that earlier Nemoto equation. And again, in block diagram form, you can see we have the system. In this case, there's a difference from the other one in that we are only using rate of turn feedback. We don't actually get any feedback from the heading itself. And that's because the model is a model of rate of turn. And so that, again, adapts based on these adaptive gain parameters and actually changes the constants of the model. So here we're adapting this part instead of the controller that we were adapting before with the course change controller. This version was found to work better with the type of vessels that we're operating because they are small and turn so quickly that trying to adapt during a turn is difficult because it only takes 2 to 4 seconds to make a 90-degree course change. And so it's difficult to have a practical implementation of a course change controller. It's much better in this case to kind of slowly calculate the constants that affect the way that the vessel maneuvers and tune the response accordingly. So this one is based on 2 parameters, zeta again as we described earlier, and then omega, which is the natural frequency of yaw. That one's a little bit harder to characterize and just has to be determined based on the vessel itself. But it essentially determines the speed of the response. So a higher natural frequency means a faster response, and these are with the same zeta, so they have kind of the same general characteristic. It just changes the speed of the response. Showing this in one simulation, we have a fixed natural frequency and different zetas. And so as we saw in the earlier equation, Kp is proportional to, so that's the part of the PID controller, is proportional to the natural frequency. And so if it's the same, all of those eventually, they're purposely started with an incorrect value of the model that it's trying to adapt to. And so it starts off and they eventually all converge to a similar value. For the zetas being different, Kd is proportional to zeta, and so they all end at different places. This ends up having the final results. So this is the simulation of a turn at the end of that last graph. And you can see the one with the low zeta overshoots and settles, and as expected, the higher take longer to settle. So we're seeing what we would expect to after the vessel's been able to adapt. I hadn't had much chance to test this on actual boats because of hardware problems and scheduling, so I made a robust simulator to try to throw some more things at it and make sure it would handle different scenarios. So I built a wave simulator into the simulation inside of the autonomy system, and you can see here the effect at different headings on speed and the heading variation based on some waves. There's also sensor noise in a lot of the systems, especially the low cost sensors like the GP9 that I'm using in my single box solution. And so I simulate some high frequency noise that's common of these systems and have a filtering algorithm built into the model reference controller. Because of the filtering, there is a delay in the signal, and so I also delay the model signal accordingly to compare them so that it doesn't throw off that adaptation. This is an example just showing kind of everything put together at once. So this has a rudder offset such that 0 degrees isn't actually straight and was started with incorrect model parameters. And over time, this one has fairly high gains, so the waves are actually affecting it. But over time, it levels out to a pretty steady model parameter, as well as this is Ki adapting to the difference in rudder. So you can see that even with this is with noise and waves thrown in, the system still behaves as expected. In addition to the heading control, I developed a speed controller. This was done from scratch on kind of different methodology based on the way that we would operate human-driven vessels, where during a survey, it doesn't matter if you maintain an exact speed, you just want to be somewhere near the speed that's desired. And so instead of making constant adjustments like a continuous time controller that we had before, it actually averages over periods. So the initial setting for the controller, when you give it a first speed that you want, is based off of a thrust map that you would have measured in advance running the boat at different thrusts. So this initial setting is enacted, and then the controller waits for both the heading and the speed to settle out so that you have an accurate measurement of what the speed's going to be at that thrust. Most likely, you're not going to get the exact speed that you measured when characterizing because your equipment's different, or there's waves, or there's a current, or something like that. So after that, it does an initial quick adjust after a short period of time to try to get you as close as possible to the correct value. And then after a longer period of time, it'll do a minor adjustment, or hopefully minor adjustment, assuming that you're close to the value. And it will continue to do these repeatedly over time, over a longer interval. When first controlling, it also takes into account an estimate of the currents, and so I'll show that later, how that actually works. This is an example of my version compared to a PID control, and so the idea is for these battery-powered vessels that you'll reduce the amount of thruster effort, because you can see the PID is trying to, so every time you turn, you're going to slow down. But unless you're slowing down to 0 and stopping your turn, it doesn't matter that much that you're slowing down for a temporary period. And so the PID controller spikes the amount of thrust to the motors every time it turns because the vessel's slowing down, whereas my controller knows when the vessel is turning and purposely doesn't adjust the speed for those periods. Instead, it's just slowly adjusting a little bit over time based on the differences in the waves. And you can see it still keeps it within a pretty tight tolerance, about 0.1 of the desired speed. Whereas the PID controller actually overshoots the speed pretty significantly, the red, because it's continually trying to adjust for things that are higher frequency than the thrusters are actually able to respond to. This is an example with currents. The controller that I developed, this is actually switched, so mine is on the bottom, but the controller that I developed takes into account measurements of the difference between its expected thrust from the thrust map and the average thrust over time at different headings. And so it tries to figure out both an estimate of the difference at different headings as well as the current overall for headings that it hasn't measured. And so you can see after kind of an initial run here with an offset, it'll figure that out, and then it will get the correct values right away the next time that it's going on a certain heading. And so it doesn't have to adjust. It stays at about the right one. Whereas the PID controller has to continually, it'll overshoot at first when the waves are against it, and then it'll go the other direction when the waves are with it, and it won't know how to compensate. This kind of just shows the estimate. In this case, I'm just driving at 90-degree angles, so it only has specific estimates for angles along those realms, and then it estimated the current here at 90 degrees and half a meter per second, which is what I had put into the simulation system. So moving on, now that we have a vessel that can actually drive along headings and at a speed that we wanted to, we needed to actually do something autonomously. So the next step is to do some path planning and build around a more extensible autonomy system. The autonomy system that I've been using for development is called MOOS-IvP. It was originally developed at MIT for underwater vehicles, and it has been extended to surface vehicles. This provides a framework for message passing architecture between different applications that are running simultaneously and communicating via a central process called the MOOS database. So you can have different sensors passing in information, processing apps, doing something with that. The IVP helm, which is a core component, actually makes the decisions for where the vessel wants to go. So that's taking in all the data that you're sensing and processing. and then eventually you'll have some sort of controller app that actually physically makes the vessel do what you want. So in my case, I've written drivers for all the systems in my custom box, as well as a lot of the systems that we've integrated with on the Z-boat and other boats. I've also written some utilities for line transfer from our hydrographic software, as well as the control system that I mentioned. When this is all put together, you can see the custom applications kind of form the entire bottom of this. Those are all things that I've developed, including the model reference controller and the simulator that involves the waves and noise, and a lot of interfaces for all the different devices that we use. This doesn't include the survey path planning applications, which I'll talk about in a separate diagram later. The MOOS-IvP, that IvP helm that I was talking about, has a set of predefined autonomy behaviors, and you can also extend it with your own, but most of what I've constructed uses the predefined behaviors in a structure, and so you can actually put together different behaviors to do things at different times and be triggered by different events. There's different pretty useful things like waypoints that'll follow patterns, loiter and station keep that'll stay in a certain location, either retracing something or trying to maintain a position. And there's also built-in collision avoidance if you have information about other vessels. This diagram kind of shows some of those put together into a mission file. So you can have the waypoints here that it's running. Then I can tell it to return to a designated home point. And then you can also use your mouse to input some things. So I can click and tell the vessel where I want it to go, and it'll follow my mouse. And then finally, you can tell it that you want it to stay in a current position by telling it you have, I call it fault for this, but you can tell it just to hold position. This general structure kind of forms the basis for all of the missions that I've built on top of that, including the path planning. You can do these behaviors in addition to everything else that's in the system. I've also been, for systems that already have hardware on board, you can eliminate even that module that's simplified with the Raspberry Pi and run the MOOS-IvP system within a virtual machine. It's only designed to run on Linux or Mac OS natively. And so a lot of the hardware that we have on board survey vessels is Windows, because a lot of the software that we use for surveying tends to be native to Windows. So I experimented with running the software, the MOOS-IvP software, in a virtual machine and was successful in doing that for some remote monitoring of the Z-boats. Moving on to the path planning algorithm that I've implemented, the first part, I would design the path planning algorithm around what we talked about for human methodology of surveying. So that's, you define a polygon area, and then the boat proceeds to automatically survey that, optimizing itself based on the depths that it's sensing, and then it figures out what to do when it gets to the end of the polygon. There's two ways that I can run this, partially due to availability of hardware. So if you actually have a swath sonar system, you can measure the width of the swath and you actually know it. If you have a single beam system, for testing purposes, you can simulate a swath width, even though you only know the depth below you. You just pretend that it extends all the way across. There's a lot of systems often output noisy data, so if there's things in the water column, they might actually sense them, and oftentimes there's side lobe interference or bubbles that will sweep under the transducer. And so to eliminate some of this, I filter the data coming in with a standard deviation away from the running mean. And so when you're on small changes, it'll accept all of the data based on a standard deviation away from the last accepted point. But if you suddenly jump up to something, it'll reject that point. Continually, you can see this is representing the standard deviation, so we're increasing as we go along. And then if we go back to the bottom, we'll accept that over time, probably decreasing the standard deviation again. The one part where you will get undesired behavior from this is if you have a steep slope, it doesn't attempt to predict any sort of slope, and so it'll increase the standard deviation and eventually accept it, as well as change the running mean, which I don't really have depicted here. Once you have those filtered known good sonar points, or hopefully good sonar points, those are recorded and then decimated for the final path planning. So as you go along the swath, you set an interval, in this case 10 meters, at which you want to decimate the swath. the minimums along that are then selected and used as the edge for path planning. So these are connected, and then this is transferred into this next diagram. So this is that edge here, based on minimums selected out of an interval. You're then going to offset that for the next path and plan a path along there. Depending on the way it's shaped, you might end up with things that are undesirable for vessel operation. And so there's some refinement that's done by removing very sharp bends that you wouldn't want to try to drive a vessel around and that would cause undesired sonar performance, as well as in areas where it has made a turn, it'll often cross itself in that offset path, and so it eliminates any area where there's an intersection with itself in the path. This could potentially, both of these could potentially leave gaps in your data coverage, but there's a way to sense that and go back and fill them in, and it's much more efficient typically to cut off these points than trying to drive yourself around in not ideal paths. So I initially built a simulator in Python that simulated both the motion of the vessel and ran my path planning algorithm. These are some examples from that where it could generate a simulated terrain, and you can see that as expected, it's spreading the swaths further apart where it's deeper, indicated by blue, and bunching them together where it's shallower. I also was able to import data into this from existing surveys. You can see here is some examples of where those paths have been cut off due to the angle limit, and it's identified where there's data gaps, and so those could go back and be addressed after the fact. So now, combining the MOOS-IvP system with this autonomy, or with this path planning algorithm, we actually can build an autonomous system for surveying with a swath sonar. So here's that MOOS portion. We take in the data, we filter it, as I talked about, and then this plans and records the depths for the next swath. That's passed on to the existing helm, along with my developed controller that actually outputs to the control, which could either be on a Z-boat, an existing module, or like my Arduino on the Emily retrofit module. This in sequence is planned so that you're driving along one path, recording your depths. For the first path, you're just driving along an edge of the polygon or a user-specified path. In between there and a designated turn point that's offset from the end of the path, the next path is actually calculated so that where it's going to go next. If it happens to get to the turn point before that's calculated, it'll just hold position at the turn point. If the vessel can't turn within the radius of the next path, some optional Williamson turn points will be put in to turn away and then back towards the path, but this hasn't been necessary with any of the small vessels that we've been using. An alignment line is put on the next one to make sure that the vessel isn't oscillating and yawing around its desired heading for ideal sonar performance coming onto the line, and then the next path is run. There's also some implementation of basic shoal safety through a procedure that we call half-stepping, that instead of planning the path offset from the edge of your existing coverage so that only the edge of the swath will overlap, you instead plan it along the edge of the swath when you get to a certain depth threshold. So you're driving over known depth data, and you know that it's not shallower than where your vessel can navigate. When you get to depths that are shallower than another threshold where you don't want to navigate, you eventually run just along the same line until the entire area is covered, and then the vessel will halt the survey. Some examples of simulation in the MOOS environment from these are from the summer hydro survey class last year, which wasn't really run with adaptive path planning, so it's not easy to compare things here, but it just gives an idea of how things are spread apart in the deeper regions and then bunched together as you get closer to shore. These examples are from NOAA surveys, and they can actually be compared with the way that we ran them on launches. The launch lines are shown here in black, and then the survey lines in white. In this case, they're fairly close, as would be expected. In this case, the survey lines seem to be much more efficient and are spaced further apart. This could just come from the confidence of the coxswain driving a certain distance away, as well as the fact that we can control this vessel a lot better than a human probably can at a finer interval. Some of the paths, if you decimate them at something like 10 or 20 meters, that's only 8 or 15 seconds of driving at a survey speed, and a person isn't easily going to be able to compensate their path that quickly. They're going to be more focused on trying to still keep on the one that they're on. So in these cases, measuring out the total, it comes actually for both of these, which was interesting, to 23% less linear nautical miles or meters of surveying. Of course, they're not completely comparable, and this one would have left some gaps, so there probably would have been another line needed to be run down here. In this case, it is pretty good in terms of coverage, and so we get about that much less, which in this larger area corresponds to over 3 hours of saved survey time. In this area, that would still be over an hour, and so especially where time and efficiency mean money, or for these smaller vessels, being able to operate them on battery for longer, that's important. We weren't able to do much field testing on the control system, but I was able to get some testing in with different boats for sonar path planning. Some of the path planning algorithms were still in fairly early stages at this point, so the behaviors are a bit imperfect, but they still give a good representation of what can be seen in the field. I was able to test with a single beam system from one of the Z-boats that the NOAA ship Thomas Jefferson had in Newport, Rhode Island. These were deployed next to the pier, and this was an area that was dredged, so it's really flat, and the paths end up being planned essentially parallel to each other, which would be expected for a flat area. Up in the top area here, this demonstrates the HYPACK line application that I have, because they had a pre-planned survey reference area. I was able to pass that into my system and have it run their reference area with the MOOS-IvP autonomy as well. For multi-beam testing, the Teledyne Ocean Science built a boat with an MB1 sonar system, swath sonar system integrated, and so are actually able to test the way that the algorithm is supposed to work for full coverage. The conditions weren't ideal for this survey, and in fact it had to be moved more inshore because it was so rough that surveying in our originally designated area would have been too rough for the Z-boat. And so it still performed fairly well considering those conditions. This is the original input of the area that I wanted to survey, and these are the results from that. You can see that the vessel in the beginning was having trouble doing some of the planning and data collection because the sonar system had so many bubbles going under it. The operator was able to tune the system along this point and get much more desirable operation of the sonar itself, and therefore the path planning looks a lot better in the northern portion of the survey. That's what could be expected under better conditions in general. And even with this, it still recovers and plans paths for the entire thing, only leaving a few holidays. This example also demonstrates one of the reasons that we're going back and prioritizing some of these shallower, heavily recreationally trafficked areas. We have a shoal detected here that is less than 6 feet along the 12-foot contour line on the raster chart. The other contours tend to agree, except for this one where the channel actually seems to have widened. We can see on the electronic navigation chart that the land has actually been updated in this area, probably from a photo survey from an airplane, but the bathymetric chart has not, and the contours, in fact, go across land. So they're obviously wrong, but no surveys have been done in this area since the, I believe, early 1900s. And so that demonstrates the need to update some of these shallow areas. Getting into kind of the NOAA specification side of things, this was able to complete the survey satisfactorily, except for the holidays, to NOAA's standard of 5 soundings per node. And you can see here, this is a data density just mapped out in grayscale, but it gives an idea of where the edges of the swaths are. And you can see there's pretty minimal overlap in a lot of these places, but we're still maintaining suitable data density. And so this is much more efficient than a person would probably be able to drive, especially when the swaths are this narrow. Was also able to operate some of the vessels remotely for trials. I was able to do this with the Thomas Jefferson Z-boats, which were operated via a cell phone modem while they were in Norfolk, Virginia, and I was here at my desk. So that not only enables trials when I don't have to be physically present, but it also demonstrates the potential application of these type of vessels to a future scenario where someone could control a lot of them, either over satellite or over cell phone modem if there's coverage available, and remotely monitor them while they conducted their path or their surveys autonomously. We're also able to do a few local tests on the vessels that we had. This shows the one example of sonar data that we were actually able to collect, and it was during some control systems testing, so it doesn't look particularly systematic. But it proved that the entire box system was able to collect the data that we wanted it to, and had we had a bit better hardware operation at the time, we would have been able to collect sonar data easily. We were also able to get Emily fully running, although difficulties with the gas engine have prevented us from doing much in terms of survey work with that vessel. So in summary, I've developed a full hardware system that's able to retrofit essentially any existing vessel as long as there's a way to control its throttle, its rudder, or if it has turning propellers, essentially control the vessel electronically. I can retrofit it and turn it into an autonomous boat. If we have the ability to gain sonar information, we can also do path planning, which can increase efficiency over human driving, as well as just simply eliminate the people from the need to run the vessel, which we often have staffing difficulties and training shortages in NOAA, so this can be advantageous both from that perspective as well as the risk perspective that I talked about earlier. We also have a new control system that should lead to robust operations in a variety of dynamic environments, which hasn't been very applied to small vessels in the past, and even large marine vessels haven't had that many advances in their control systems since the early 1920s when PID control was first integrated into large vessels for transits. So together, all of these put together starts moving us towards a more routine use of autonomous vessels in the field and a simplified use through additional autonomy on top of human plans, so that we don't have to plan out all of the lines in advance. We don't have to rigorously check all of the areas to see if they're too shallow or too deep. It'll just give it an area and more than likely do the survey the way that you want it to. There's still a little bit of work that we can do on all of the system. There's fault detection from the control system because of the fact that we know what the expected speed is and we're able to detect what the running speed is. You can determine, for example, if a propeller has been jammed, which often does happen on the Z-boats. They have exposed propellers that pick up a lot of marine debris. There's also the ability to characterize, or there could be the ability to characterize environmental disturbances, so actually trying to model the effects of wind and current into the control system and therefore compensate for them better than the current system is able. The path planning at the moment doesn't deal very well with isolated shallow areas, so if there's a pinnacle in the middle of your survey that the boat isn't going to want to go around, it'll continue surveying on one side of that until it essentially either finishes the survey or gets stuck somewhere. So I haven't been able to address those type of issues, or in complex areas. A lot of people, like the single beam planning that I talked about in the beginning, have already tackled how to deconstruct complex polygon areas into more simple regions to be surveyed. So that problem could be integrated into this system. In overall autonomy, to increase the effectiveness of these vessels and simplify operation towards that goal of just being able to deploy them and have them conduct their mission, we need to increase the situational awareness of the vessels in terms of sensing capabilities of other vessels in the operating environment, as well as just the boat itself and how it's functioning. We also, a lot of the user interfaces right now, both for commercial systems and for this MOOS-IvP system, are not very user-friendly. They require a lot of code or text written files to configure them. And so once you figure that out, it's very flexible and capable of doing pretty complex missions. But if you just want to run your boat, it's fairly difficult. And I've done some work towards simplifying this by writing scripts that'll generate my path planning areas. So you just really need to type in the area and the lat long of the general region that you're surveying, and it'll automatically put all of that into these text mission files. But there's still a lot of work to make that simple for operators in the field. So throughout all of this, I've had a lot of help. The NOAA has supported me both in the research and through giving the vessels and purchasing the sonar system that I've been using. The NOAA ship Thomas Jefferson has been very gracious to give me a lot of time testing on their Z-boats, both remotely, and I was able to spend some time there in person last summer. Dr. Rankin comes from the Naval Undersea Warfare Center, and they've also provided funding support to the project overall. And some of my conference and travel support has been funded by the grad school. And with that, I'll leave you with a little video of some path planning and kind of, this was from the early stages, but and showing some of the videos of the vessels in operation.
But we have to, we'll open up the questions for the general public, but we have to minimize that time because Dr. Rankin has to peace out before 10. So, any general questions at this point? What was that?
I said I pretty much fit it.
I was wondering, we were talking about filtering your swath data, and you pointed out you were going to have an issue if the slope changed dramatically because it would throw off the standard deviation.
Right.
I feel like in sort of shallow areas where you'd like to deploy this, you're going to have that issue very often. So I was just wondering if you could talk about what you were planning on doing to address that in the future if it hadn't been addressed.
Yeah, I mean, so there could be more complex methods of filtering that you could introduce. Right now, it's pretty simple. The way that it deals with that over time is it's actually an time-weighted, exponentially decreasing both mean and standard deviation right now. And so if things are increasing quickly, that'll be quickly incorporated into that mean. And so it'll eventually it'll incorporate that data. The original way that I had it would take a certain length of time, and if it hadn't changed within that time, it would essentially assume that it was, the new depths were correct, and it would take the mean from those. So some sort of approach in between those two could be used as well.
I have a couple questions about your control side. You were looking at, for both your controllers, you were examining different values of zeta and looking at how it was damped.
Right.
I'm just wondering, what was your metric for choosing? At some point, you have to choose one.
Right.
What's your metric for choosing that?
I chose them based kind of on the way that I want the vessel to operate, right? But the way that seems to be most desirable in operation is a zeta around 0.7 or 0.8. So it corresponds to a little bit of overshoot, but a little bit quicker turn. These small vessels settle fairly quickly after that, and the turns are so quickly that a little bit of overshoot doesn't matter too much, and it gets them online quickly as well. So that tends to yield good behavior, but you can set it to whatever if you want it to turn slowly and not overshoot at all, you can set it to 1 or a little over 1, and it'll behave as, I wouldn't set it much lower because you don't necessarily want oscillation on the lines, but somewhere around 0.7 or 0.8 tends to behave well. That I just saw through trials and also through kind of reversing, so that the equation for that in terms of Kp, originally when I was just testing with the PID controller, I was seeing that Kp, so Kp and the Kp in this is related to zeta. There we go. Yep. So using the Kp and Kd that I had determined to give a good response for the vessel already through testing, I kind of reversed that to get out my first values of zeta and omega. Because omega especially is difficult to characterize physically. Any of the resources I tried to look up on that all give it in terms of these parameters. They say, oh, it's based on K and tau. Well, okay, but I'm trying to determine K. So essentially it's just a fairly, some claim it varies depending on the length of the vessel, but I didn't find that to be completely true or not linearly. So it's not a well-characterized constant, so kind of just needs a little bit of experiment. And so I got that from KPs, that KPs around 1 to 1.4 tended to work best, so I can then reverse out what omega would be for that.
So is it fair to say it's a little bit trial and error to see how fast you get on the
right heading? Yeah. So omega is essentially, if you set it too high, you're gonna attempt to do something that the system can't physically do. So ideally, you would want to set it near the limit that the system can do, so it'll turn as quickly as possible and use full rudder for as long of a time as possible without mischaracterizing that, because then your adaptation won't work very long.
So another question along the same lines that I had is, when you look at your robust control, I think you had maybe wave action or something like that, and you were looking at, I think it was your second controller, you're estimating your coefficients for your PID controller, and yeah, that one, and you see that I'm looking at the two, what are they, orange and yellow lines, and they're noisy looking. I mean, they've converged to some average value, but they're noisy looking, and I'm wondering if I'm assuming that noise is just, it's that you don't want that noise in those coefficients. That's not real. It's just due to the waves.
Yes.
And is there a more robust way you can estimate those coefficients to, add in, assume that there's going to be some noise and partition that out, or low pass filter it?
I mean, so I'm already kind of trying to do that, right? So I'm filtering out. I don't actually want to filter out the waves, because the effect of that on the rate of turn is real, but I'm actually filtering. So there's some things that I do already to get around that. If the rudder angle, so I only, because the signal to noise ratio is low at low rudder angles, meaning that the boat doesn't turn very much, and it's more likely to be affected by things like waves at low rudder angles, whereas at high rudder angles, it's more likely that the majority of the rate of turn signal is coming from the rudder itself. I don't use anything that's at low rudder angles below a threshold, which I've set typically around 10 degrees. I just don't adapt if that's the case. So most of the adaptation is going on during turns. In this case, it also depends on how high you set those adaptive gains. The alphas and betas in these equations. In that example that I was showing, I purposely set them higher than what you would probably want to operate a vessel, just to make it converge quickly and show some of that behavior. Usually for smoother adaptation, if you set them an order of magnitude lower, you'll get a much less of a response. You'll still get a response, but it'll be an order of magnitude lower. I also don't use the updates from those controllers or from that adaptation during a turn. So I fix KP and KD at the beginning of a turn and don't change them, so that the characteristic of the turn itself isn't affected by waves or incorrect adaptation that happens during the turn. And typically the effect, if any, tends to be canceled out going one, so because it's a periodic nature, it'll be bumped one direction, but then it'll be bumped the other direction going the other way around on the turn. And so by the end of the turn, they actually tend to settle fairly well. So there's a few things that I've built in just through experience and playing around and seeing things that didn't really work that try to overcome some of those things already. And there's certainly more things that could be done, but it does tend to work fairly well, especially if the idea here was I purposely set the initial constants wrong. If you were able to run a vessel for long enough that you knew pretty close to what they should be, the idea is that this just has to really do the fine-tuning and long-term tuning. And so this is trying to tune it over something like 100 seconds. You don't really need your environmental processes, and you're not draining your fuel that quickly that you need to adapt in 100 seconds. So if you're close initially, you can set those gains much lower, and you'll only see it essentially will be coming low-pass filtering.
Those gains with the alpha, beta.
The alpha, beta, yeah.
Okay, so I'm going to stop there. Really quick question? Is that a really quick question?
We had one from the web.
Oh.
Could we try to slip that one
Sure.
in?
Okay.
Douglas Wood asks, what was the depth range of the area that you did the line driving efficiency comparison? And to that, and what were the compared platforms? So the line driving efficiency is two different platforms. The one on the left side is Reson 7125, and on the right, actually no, they're both. Yeah, I believe they're both 7125, just operated at different times. The depth range on the left is about 80 meters in the deep part and 40 or 50 in the shallow. The other one, which you can see by the more uniform lines, the color range kind of throws it off, but it only goes between about 80 meters and, well, the shallowest portion on the south end is maybe
50 or 60, but most of it is within about 70 to 80. It's not too big of a depth difference.
All right, we're going to cut it off there. Let's thank you.